Hi there guys, today we are going to go through a school examination paper. So this is not the typical sort of NCEA previous year's external paper that I normally do on my YouTube channel. So this is, I thought I'm going to go do this for my students anyway, because this is a school exam that we did for level 3 Chem aqueous standard, and they didn't do so well. So I thought, I should really go through these. So if you haven't done this set of questions, like say if you're from another school and you look at these questions like, this never done this before, so this is a really good opportunity for you to, just feel free to pause and give the question a go yourself. But otherwise, if you have done the questions yourself and didn't do so particularly well, we can spend the next 20 minutes or so and go through this particular set of questions. Okay, so let's just get started. So question 1, we are going to write the equation equilibrium occurring for saturated solution mx2. So m is just a fixture element, so it doesn't matter what it is. So that just means mx2 as a solid is going to partially dissociate in water, turning into m2 plus 2x minus. So both of these are aqueous. So this is your typical AB2 type of, like say AB2 type of sparingly soluble solids. So it just means, when they dissolve, they separate into the two ions, and well, in this case, one is 2 plus, one is 1 minus. Okay, now write the expression for Ks. So Ks is even easier. Ks is just m, the concentration of m2 plus multiplied by the concentration of x minus to the power of 2. So remember, it's the coefficient becomes a power. Yeah, I mean, you should, most of the year 12s already know this, so yes, year 13 you should really be not struggling in this particular section. Now calculate the concentration of x minus ions, if Ks is 1.84 times 10 to the power -7. So this is your typical Ks, because this is an AB2 type, so you can just go Ks equals 4x cubed. So 4x cubed equals 1.84 times 10 to the power of -7. So how do I solve x? So that means you use 1.84 times 10 to the power -7. Use that divided by 4 first, and once you divide it by 4, you cube root this particular number, and the concentration, so in this case x, so now I want to make it clear, this x is solubility, not the actually let me change it so it doesn't confuse some of you. I just realized, because normally I just use x. All right, so let's use a different letter. Let's use s. So s stands for solubility. It's the same thing like, Ks equals x squared, same thing as Ks equals s squared. Ks equals 4x cubed. Sorry, 4s cubed. They mean the same thing. The s stands for solubility. Okay, now there's a reason why I want to do this. The first things first, we figure out the solubility. Very easy. You just use 1.84 times 10 to the power -7 divided by 4 first, and then take a cube root, and then your answer should be 0.00358 moles per liter. Now this is where a lot of you would have stopped, because you will go, I calculated the solubility, yay, I've done everything I've been asked to do, which is incorrect in this case. We ask you to calculate the concentration of x minus, so we want you to calculate the concentration of that. So if we go back here, if we do this s, so in this case, the m2 plus is going to be 2s, and then the x minus here is going to be, the solubility here, the m2 plus is going to be s, why am I keep running force, multiplied by 2s to the power of 2. Now why is that? Because you can look at this equation here, you can see that the x minus concentration, so for every mole of mx2 that dissociate, you make twice as many moles of x minus compared to your m2 plus, because x minus is is 1 to 2 ratio. So that means when you want to, so what we actually calculated, we calculate the solubility of the solution. So this means when, so let's just break it down. Oops, break it down. So this is M2 plus 2x minus. So this means if I have 1 mole of mx2 dissolving, I'll make 1 mole of m2 plus and make 2 moles of 2x minus of x minus. Okay, so if we know the solubility is thus, this is going to be 0.00358. This is going to be 0.00358, and they're wanting you to calculate the concentration of x minus, which is going to be 0.0358 times 2. So that's going to be 0.00717. Okay, so that's 3 SF and moles per liter. So you just need to do one extra step here, because that's a tricky part of this particular question. You need to look at the question. The question asks you to calculate the concentration of X minus ions. So yeah, you know, we always do Ks equals X times 2x squared, and that's how you get 4x cubed. So what does X stand for? X stands for solubility. So when we did this equation, I think a lot of my students can figure out this, but then they didn't read the question. I actually want to know this concentration, so you need to double that. Okay, so that's that particular question. A bit tricky, but definitely doable. I'm gonna block out this section here. All right, so what is the mass of lithium chloride that's required to form a saturated solution if it's added to 50 mL of that sodium carbonate? Okay, so the solubility, the Ks of Al2CO3 is given. Now this is the thing that you should always use the question. Read when you look at the question and you don't know what to do, look at the Ks expression, because we don't give you the Ks expression of Li2CO3 for no reason, because you obviously need to compare the two values, because the Ks, like I mentioned in multiple of my examination videos previously, think about the Ks as your the university entrance, and then you look at your ionic product. Okay, so the ionic product is what you actually get for your results from NCEA, for example, and then you compare your ionic product versus the Ks. If the IP is bigger than Ks, then yeah, you graduated, you are good to go, you have dissolved, you precipitate out of school, you can leave. Okay, so to make a saturated solution, we want our IP to be exactly equal to Ks. Okay, so in this case, because the question asks us to make a saturated solution, so it just means we want to dissolve just enough of the lithium chloride in the sodium carbonate to make Li2CO3. Okay, so really quick, so what do we know? We know the concentration of CO3 2 minus, which is 0.105 moles per liter. That's given. Okay, now what are we interested in? We're interested in here Ks Li2CO3. So this is the thing that the advice that I give to most people. Just look at the Ks expression. We don't give you that for no reason. Okay, so if you look at Li2CO3, and if you get confused, you can just do this. Just write this equilibrium, and if you can't write that, then you really have to go back to the basics, and then Ks equals Li plus squared multiplied by CO3 2 minus. Okay, so this is the absolute basic, so you should be able to write this particular equation. So what does that number equal to? That number equals to 8.15 times 10 to the power of -4. So we know here, can you see what we're doing here? We know the concentration of CO3 minus. We already know this. We know this. We can figure out the concentration of our lithium ion. Okay, so we can just make it x, so we can just go x squared times 0.105 equals 8.15 times 10 to the power -4. Don't get confused with the saturated solution. It just means, yes, you have just dissolved it, you have added enough, and this is, all of it has dissolved, no more can dissolve. It has now become saturated, it has reached equilibrium, and then you have reached this particular Ks. Okay, so once we solve this, x equals 0.0881 mole per liter, and that's your the concentration of Li plus. So Li plus concentration equals X, which is 0.0881 mole per liter. All right, so we know the concentration of Li plus. We know the molar mass of LiCl. We know the anything else we know? We know the volume here. Do we need the volume? Not really. Okay, so actually we do need the volume, because I mentioned, and again I mentioned this multiple times before, all the numbers that we give you in chem, especially in aqueous, you tend to use them once. Okay, so we know the concentration, we know the volume, we know C, we know V, we can figure out the mole. So that's going to be 0.0881 times 0.05 liters, which is going to be 0.00405 moles. Sorry, 4405 moles. So you now know the moles, you know the molar mass. So because what is the question trying to ask you? The question is trying to ask you what is the mass of lithium chloride that has, that is required to reach this particular saturation point. So what do we do here? So this just means N equals small m divided by big M, and which equals to small m equals N times big M. So just going to be 0.00405 times 42.4, and then you get 0.187 grams. Okay, and if you actually go back and check all of the working and look at all the numbers, you would have used every single number that the question has given you once. Okay, so you don't need to use them multiple times, and this is the biggest part of the clue they can give you that really stands out. They give you the Ks, they don't give you the Ks for no reason. Okay, they don't give you the 50 mils for no reason, and that mole, that mass, you should be able to look at the mass and go, all right, I need the small m. And what equation do I know from year 12 and year 13 chemistry is N equals small m divided by big M, and I know the big M, so you need the mole. How do you get the mole? You're dealing with concentration, so you need N equals C times V. You know the volume is 50 mils, so what is the concentration? Well, actually, and then you write the equilibrium constant, and then you can see that you can work this out. You should have plenty of time with the aqueous. Like I mentioned before, 40 minutes is all you need to get 24 out of 24 for aqueous if you know what you're doing. So time shouldn't be a constraint here. Okay, so 0.187 grams. Next one. Now, calcium. So like I mentioned before, feel free to pause and give the question a go yourself. And if you struggle, then we can. Then you can just hear me explaining it. All right, so let's have a look at this question. Calcium hydroxide is partially soluble. The pH of a saturation is 12.8. Calculate the solubility. Okay, so pH equals 12.8. That means we can calculate the concentration. Now, do we need to calculate the solubility of calcium hydroxide? Okay, so the pH is 12.8. So that means we can figure out the OH minus concentration. So here we go. So let's figure out OH minus. Why not? So the OH minus concentration. So we can do it different ways. So we can go 14 minus 12.8 to give us 1.2, and then the OH minus is just simply 10 to the power of negative 1.2, which is going to be 10 to the power of negative 1.2, which is 0.0631. Oh, I don't know why I left a massive gap there. 0.0631 moles per liter. Okay, so from this particular question, just from the pH, you can find the OH minus concentration. And you may go, why the heck do I need the OH minus concentration? Because we're dealing with calcium hydroxide, because we are dissolving. So again, whenever you are lost, you will need to use the equilibrium that we're looking at here. So calcium hydroxide will partially dissociate into Ca2 plus and hydroxide ion. So that means the Ks equals Ca2 plus multiplied by the OH minus concentration to the power of 2. Okay, so you can see, now we know the OH minus concentration. Now I'm just going to do this the longer way because I think that probably makes a little bit more sense, because I don't want you to get confused. Like say for example, if X moles of calcium hydroxide dissolved, I will make X moles of Ca2 plus, I'll make 2X moles of hydroxide. Okay, so I think all of you should be able to do that. Now, can you see the OH minus concentration is twice as many of the Ca2 pluses? And I already know the concentration of hydroxide. So that means my Ca2 plus concentration is simply going to be half of that number that we just calculated, which is going to be 0.0315 moles per liter. All right, so I know this. Let's just calculate. So that means, why do I even need to calculate the case? I don't even know. What do we need here? Oh, I just already got the concentrations. What do we actually calculate? Calculate the solubility. Oh, we did it. The solubility is X. If I make that X moles makes X moles makes 2X moles. So if I know, so the solubility equals X, which is equal to Ca2 plus, which is just 0.0315 moles per liter. And what do they want? They want me to convert that in grams per liter. So to go from moles per liter to grams per liter, you use the molar mass multiplied by the moles per liter to give you grams per liter, which is 2.34 grams per liter. I don't even know why I was doing the KS. Because it's just not needed. So in this particular question, it's a bit, I like questions like this. It's just a bit out of the ordinary. So if you got given the pH, you find the OH minus concentration, and then you should understand that the OH minus concentration is twice as big as the Ca2 plus. So you can divide it by 2 to find the solubility, which is equivalent to the calcium ion concentration. And don't get confused, like what is solubility? Solubility is how many moles would dissolve in 1 liter of the solvent. So that's where the X comes in, that's where these X's comes in. So when X moles of calcium hydroxide dissolved, which is solubility, I make X moles of Ca2 plus. So that's why the solubility and the Ca2 plus is equivalent, because it's a 1-to-1 mole ratio. Okay, so hopefully that one's going pretty good for you. All right, let's just move on. Next one. A small amount of zinc hydroxide powder is immersed in a saturated solution of zinc hydroxide. Wait, why would you put zinc hydroxide into zinc hydroxide? It's just silly. Discuss in terms of equilibrium principle the changing effect of pH, concentration, species, blah, 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 blah. Okay, so I'm just adding addition a few drops, then X is sodium hydroxide solution. So this is your this is where you need to look at your look at your resource sheet, because on your resource sheet you will see a complex sign of Zn OH4 2 minus. You will see this complex sign as one of the list. Okay, so if I'm dissolving, so you need to look here, it says addition of a few drops then excess sodium amount. So that means there are 2 processes that you need to look at here. So let's have a look at this. So the first part that we need to do is you need to understand we are dissolving zinc hydroxide. I'm just writing, this is not the full answer. I'm just gonna walk over this. I'm not gonna write all of the entirety of the answers. So this is the equilibrium. So if I want to dissolve this particular thing in sodium hydroxide, you can see the hydroxide is a common ion. Okay, so initially, if you add this particular solution, add this into zinc sodium hydroxide, which has a lot of the sodium and a lot of the hydroxide, then you have a common ion effect. Okay, so if you have a few drops added in at the beginning, that means the equilibrium will shift. So we'll look at this top equilibrium. Yeah, so equilibrium is going to shift to the left. Okay, so it's going to shift to the left to because there is already a lot of OH minus in the sodium hydroxide, so this concentration will increase, therefore it's going to shift to the left to use it up. Okay, but if you add excess when there are tons and tons of hydroxide, that means the Zn2 plus ions and the OH minus ions, which is abundant in the solution, you are then going to make this complex ion. So just the word excess here gives it away, and then you just need to go on the resource sheet and hunt for the complex ion. You got the zinc, you got the hydroxide, it should be a no-brainer that you are going to form this particular version of the complex ion. So what does that mean? That means your Zn2 plus concentration is going to decrease. So the Zn2 plus that's being produced, so the moment you dissolve any zinc hydroxide, the Zn2 plus is gone. Where did it go? It's going to go hang out with the excess amount of hydroxide. You're going to make this aqueous, this complex ion. So what does that mean? This Zn2 plus is gone, then the system is no longer at equilibrium. It's going to shift to the right to make more Zn2 plus, and as a result the solubility increases. Okay, so that's that part there. I mean, you can always go through some of my older videos, just look for some more detailed answers, but I'm just going to speed run this a little bit quickly. Now, next part, again, a few drops, then excess ammonia solution. Now, with the ammonia solution, it's exactly the same thing. Now, ammonia is a weak base. So what that means, if it's a weak base, it's going to partially dissociate. You're going to make NH4 plus, and you're going to make OH minus. So again, if you're only adding a few drops, remember the equilibrium that we looked at before. This is the Zn zinc hydroxide equilibrium. Can you see the OH minus is the complex, it's a common ion. If you only add a few drops of the solution in there, this equilibrium, this OH minus concentration is going to increase. It's going to shift to the left to use up the hydroxide. So, you know, the solubility actually decreases as a result. Okay, the solubility decreases because the Zn hydroxide concentration would increase as a result due to the common ion of the hydroxide. But then if you add excess, this is where you need to go on the resource sheet. You will find that, again, you don't get given the equation, but you should be able to figure out what they are just by looking at the formula of these complex ions. This is the complex ion of zinc and ammonia. This is given to you. So as you can see, if I have excess, so that means I have tons and tons of that ammonia, ammonium, what's going to happen is that the zinc hydroxide, which is sitting in the solution as a dissolve, is going to get taken away by the ammonium to make this particular complex ion. So that means this concentration is going to decrease. That means it's going to shift to the right to make more of the Zn2 plus, hence the complex ion, hence the solubility increases. Okay. So let's just move on. That's one of the really popular questions in the exam, so you can go through that quite easily. All right, question 2. Question 2 is very straightforward. This is just looking at different points of the different parts of the pHs on the titration curve. So here's 20 moles of that, a weak base, and then titrated against that, so you can see the concentrations are different. So this is why it's really important. If you don't know how to do these, because I'm not going to spend as much time compared to one of my, compared to my concept videos, go back and watch those. Okay, so but I'm just going to do this a little bit quicker. So you got given the pK, you got given the concentration and the equation. Calculate the initial pH. So initial pH is before anything has been added, so that means we are looking at this particular part of the pH. So this is a weak base. It's a weak base, so you go pH, pH, you go H3O plus equals to the concentration of Ka times Kw divided by the concentration of the base. That's the equation. Memorize it and just use it appropriately. So what's Ka? Ka is going to be 10 to the power, so if you got pKa of 10.64, Ka just 10 to the power of negative 10.64 times Kw, which is 1 times 10 to the power negative 14, and divided by the concentration of base, which is 0.0496. This is just looking for numbers, okay? So if you can't find these numbers, then I really can't help you. And that should give you, let me just quickly run these numbers in my calculator, 10 to the power of negative 10.64 times 1 times 10 to the power of negative 14 divided by 0.0496, then square root this, then you got 2.15 times 10 to the power negative 12. Remember, this is H3O plus, so pH equals negative log H3O plus, and then just negative log that blob, and that's going to give you 11.7. Done. Okay, so just it's a matter of identifying it's a weak base, okay, and then just memorize the equation, chuck it in, look for the numbers, and then there. Very easy merit for that particular question there. Now calculate the exact volume of HA at equivalence point. This is again very simple. If you understand how at equivalence point means that the moles, let's just write the equation down. CH3 and H2 plus HA goes to CH3 and H3 plus A minus. So what it means at equivalence point means that the mole of CH3 and H2 and the mole of HA are exactly the same. So at equivalence point, that's what it means, equal. All right, they equal. So they are equal amounts. So therefore this is gone, and then you made the other stuff on the right hand side. So what do we know? We, like, again, it's highlighted here, we know CH3 and H2's mole number. How do we do that? We just go in equals CV, which is 0.02 times 0.0496, which is going to give us the mole for CH3 and H2, which is going to be the equivalent 0.00992 mole. We know this mole, so this is going to be 0.000992. Now we know the concentration of the other one, which is 0.553. So you just use, so the volume is just going to be 0.000992 divided by the volume, by the concentration, sorry, which is going to be 0.553, and that's going to be 0.0179 liters, which is 17.9 mils, roughly 18 mils. Okay, so you just need to understand at equivalence point, the two moles are the same. You calculate one mole, you get the other mole divided by the concentration, you know the volume. Now calculate the pH at equivalence point. So we already done the hard yard, we already done some of the stuff that we need to do. I'm going to do the long way, just to show you how to do it. I might cheat a little bit because we already calculated some of the answers from previous part. Okay, so again, pH at equivalence point, it means this is gone, and you have this guy. And this will put, and this CH3 NH3 plus is the conjugate acid of that. That means this will partially dissociate to turn it back, and then you make this. So that means pH is not going to be 7. Okay, so we already calculate the moles. So at equivalence point, so equivalence point means when I have X moles of this reacting X moles of this, I make X moles of that, and then X moles of this. Let's just use a different color. So when I have X moles, oops, different color please. It's not giving me different color. Why aren't you giving me different color? Don't you hate it when technology doesn't work for you? Come on, computer. Come on. Why don't you like it? Work for me. Did I lock it accidentally or something? Well, I'll just do it like this. Alright, so if this is X, alright, so that means we already calculate the mole from previous parts before. So we already know the mole from here. So this is going to be 0.00992. This is going to be 0.00992. This is going to be 0.00992. Okay, so this is gone. So that means my CH3NH2 concentration, my concentration for CH3NH2 is going to be the mole that we just got from previous calculations divided by the total volume. Okay, so that means we had 20 mils from the thingamajiggy, what do you call it, the pipette in the flask, plus the 17.9 mol from the burette. Why did I? Man, this is really bugging me. How this is not letting me changing. I don't even know what happened. 0.002 plus 0.00179. So that's a total volume. This is in the burette, in the pipette. This is from the burette. This is a number that we calculated just now. And then if you use that divided by each other, you will get 0.0263 moles per liter. So this is the concentration of the weak acid. And then we just need to calculate the pH. So the pH, the pH, how do we do that? H3O plus. So this is a weak acid weak acid calculation now. So that's going to be just Ka times the concentration of the acid. So we'll just substitute numbers in. What's a Ka? I think Ka from previous one was, where's the Ka? Let me find it. pKa is 10.64. So pKa is 10.64. So Ka is 10 to the power of negative 10.64 times the concentration of the acid. And that's going to be that. And if we square root this number, that should give us 7.76 times 10 to the power of negative 7 moles per liter. Let me just double check on my calculator. 10.64 negative 10.64 263 square root. Yep, that's exactly right. So you got the H3O plus, so that means pH is negative log that, not negative log that, so it's at 6.11. Okay, so I'm definitely not saving enough space for this. Now, next question, calculate the pH after 30 mils of HA has been added. So 30 mils, so you need to understand this is the total volume. The total volume, so this thing is diluted, all right? So the concentration, so the initial concentration was 0.0553. This is in the equation. You can scroll, go back up and find this particular equation. This concentration. Now it has been diluted. Okay, so it's going to be 0.553 multiply by the volume beyond equivalence point, which is going to be 30 minus 17.9, and then the total volume, which is 30 plus 20. Okay, so you may get a little bit confused with the number. So we added 30 mils of HA. So in my flask, I have 30 mils of the HA. I have 20 mils from my pipette. And then the top number is I used 30 mils. The total volume is 30 mils. I spend 17.9 to neutralize the existing base, and the leftover is responsible for the pH. Okay, so once you've done that, and then just so this is going to be equal to 0.0133 moles per liter, and this is a strong base. A strong acid here, so you simply just go negative log 0.0133 to give you 1.88 pH. Okay, so again, sorry it's a bit rushed, but I don't want to make this video an hour long, but you can, if you get stuck with any of this particular section, just always go back to my concept videos, where I spend far more detailed hours in explaining these. All right, next one. Now explain why the pH does not change significantly between the 5 to 15 mils buffer. Okay, so look at what I did for the buffer section. So I'm not gonna do that part over here because this is dragging on a little bit. Now this one's actually quite interesting. So with reference, the equivalence point is about 18 mils. Okay, so let's have a look at the sorry, I just need to find the pH equivalence point. 18 point pH equivalence point is 6.11. Okay, so pH at equivalence point is 6.11. We calculated that before. Okay, now normally we want the pH, we want the pKa of the indicator to be plus minus 1 of the pH. So that means we want ideally something between 5.11 and 7.11. And if you look at these these three indicators, they all suck. All right. So these two are way too low, and this one's way too high. Now, which one do you choose here? Well, ideally, if I can choose, if I have to choose one, I wouldn't. You know, if I have to choose one, then yeah, I have to. You know, I pick thermal blue. But ideally, I wouldn't choose any of them because they all suck. All right. So this is like it's like the politics in New Zealand. You know, just choosing the better political party of the worst of them because they all suck, to be honest. So he's just trying to pick the one that doesn't, you know, that still kind of works but not ideally as you would hope. So which one would you pick? You pick this one. Why? Because we want an indicator to change color around the equivalence point. Okay, you don't really want to. You don't want it to change pH. You don't want it to change color before equivalent point even happens. Like if you look at these two actually change color before it actually happens. So that it's just a really poor indicator. You want it to be near the steepest part of the curve. So it's kind of like this is sorry, it's not the base curve. This is a titration curve, and one is over here, one is over here, one is over here. So you kind of like, this one sucks, this one sucks. I'll probably go with that one because that's still kind of near the steepest part of the curve. So yeah, it's not the best question. Normally just pH plus 1 plus minus 1. You want the indicator to change color around equivalence point. If you have to pick one, you normally pick one that's the closest to it. Okay, so you may even argue, you may go 4.7, like you may go crystal green at 4.7. That's close enough to this. You know, I could go with that one. Like, to be honest, if you ask me, I personally think that's okay as well because that's quite close to the curve. But ideally, again, you want the solution to change color after it has reacted. So preferably, you know, if you have to choose, afterwards is a little better than beforehand. Okay. Now, question 3. Oh my god, this video is dragging on a little bit, isn't it? Question 3. We want to calculate the phosphate buffer solution is a buffer, yay. Blah 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 blah. What do we want to do? Calculate the pH of the buffer. Okay, so we'll put this and this in a 500 ml volumetric flask. So first thing first, we need the mole. So we need the mole for this guy, which is going to be 3.5. Oh my god, the formulas are so similar. Alright, let's just highlight them so we can see which one's which. Alright, so this one is 0.43 grams of that, which is that. Yeah, so we'll just do that one first. So the mole for the one that I highlighted is going to be 0.43 divided by 156, which is 2.7564 times 10 to the power of -3 moles. Okay. Now I know the mole, I know the volume, so the concentration is going to be C equals N equals CV. So this is going to be that number divided by 0.5, which is going to be 5.51 times 10 to the power of -3 moles per liter. Now this is the part that I really hate when some students do aqueous, like that. You don't even need to be a level 3 chemist to be able to do this. You see a mass, you see a molar mass, turn it into the mole. If you can't even do that, then I really don't see what you've been doing for the past 2 years. I mean, that's just habit. Like if you see grams, you should the idea that grams is useless to a chemist. That should be embedded in your brains. You see mass, you see molar mass, turn it into moles. Everyone should be able to do this. Don't leave your question blank. All right, now let's do the other one. You can see how irritating I am with this particular part because it's so basic. Like, you spend another bloody internal on this in year 12, yet you can't do this as a level 3 chemist. All right, next part. So this mole is going to be 3.56 divided by 358, which is going to be 9.94 times 10 to the power negative 3 mole. Again, you got the mole. You can figure out the concentration. Again, divide them by the same number, divided by 0.5 liters, which is 1.99 times 10 to the power of negative 2 moles per liter. Okay, so you got the concentration for 2 of them. And what do we want to do now? We want to calculate the buffer. We want to calculate the buffer solution. In the buffer solution using this. Okay, so you can identify which one is the acid. So we got given the Ka. So even though if you can't do that, see the Ka, like see there, KaH2PO4, which is this one here. Sorry, it's a little bit hard to see now. Let me just, oops. Let me rainbow color it so you can see it. So this Ka, that means whatever is inside the bracket is an acid. Can you see this is exactly the same thing as that one there? Okay, so that means the yellow stuff, this thing here that I'm highlighting right now, this is the acid, and the one that I'm highlighting green, this one is the base. Okay, so what is the buffer pH calculation? Buffer is pH equals pKa plus log base over acid. Okay, so what's a pKa? pKa is 10 to the power, well, it's negative log 6.3 times 10 to the power negative 8 plus log, which one's the base? 1.99 times 10 to the power negative 2 divided by 5.51 times 10 to the power negative 3. Okay, so that's that, and pH should be 7.76. There. It looks really intimidating, but you just need to get to the basics. You get the mass, you get the molar mass, turn it to the mole. You got the mole, you always need the concentration. Like, this is what I meant. Every single year 13 students that's doing aqueous should memorize these equations. This is the equation for buffer. Remember it. And then obviously you need the concentration. So if you don't know the concentrations, you need to figure it out. You got the moles, you got the volume, figure them out, and then you can just substitute the numbers into the equation. Okay. Now, whether the solution will be more efficient against neutralizing small. Okay, so this is one of the old exam papers. So the pH of the buffer is 7.76. pKa is negative log 6.3 times 10 to the power negative 8, which is going to be 7.2. Right, so you just compare your pH and pKa. Can you see your pH is larger than pKa? Okay, so your pH is bigger than pKa. That means there's more, the concentration of HPO42 minus. This is just math, because you got that fraction. This is a ratio of these. So that means you have more base compared to the acid, more base. So this is more efficient against added acid. Okay, so this is more efficient against acids. Okay, because there's more base in there. You just need to remember, if the pH is bigger than pK, there's more base. Okay, and it's obviously stronger, more efficient against acids. Now the last question, this is just a silly question. This makes the paper super long if you didn't notice already. All contain equal volumes of reagent, so justify the difference in pH, conductivity. Now these solutions are all good conductors. Let's just write it down first. HCl plus CH3NH2. This will neutralize into CH3NH3 plus Cl minus, and then your CH3NH3 plus is going to partially dissociate in water to turn into CH3NH2 plus H3O plus. So this is solution P. And as we can see, what is the final pH going to be? This pH is going to be lower. This is going to be a weak acid, so the pH is going to be the pH will be below 7, but not that low, because this is a weak acid, because it's partially dissociate. And what about the conductivity? It's a good conductor because you make tons of these free moving ions. Okay, Q, CH3COOH plus NaOH makes CH3COO minus plus Na plus H2O, and then this CH3COO minus is again going to partially dissociate in the water that you just produced with it to make that plus OH minus. Okay, so your solution, you made OH minus in the dissociation, so this is a weak base. So this pH is going to be above 7, but not that high. Okay, again, you made so many of these free moving ions because this is complete dissociation, complete neutralization. Therefore, you are going to have a really good conductor as well. Look at the last one. R is HCl plus NH3. This is just going to be NH4 plus Cl minus, again neutralization, and NH4 plus is going to partially dissociate, turn into NH3 and H3O plus. So you make this partial dissociation. This is a weak acid, and then pH is going to be smaller than 7. And because you made tons of these free moving ions, it is a good electrical conductor. Okay, so that's our school exam paper. As you can see, it's very long. A lot of the students complain at the end, which is perfectly understandable if you ask me. But that's that, and it's much longer than I anticipated to be. But I hope it was helpful, because some of the questions are actually quite interesting, and I know for sure that my students definitely would definitely watch this one, because they like I said, didn't do so well in their school exams. Okay, so I will definitely be doing some streaming before the school exam, before the end of the exams. So just stay tuned, and I'll see you guys later. Take care. Bye bye.